Welcome to our second video of Unit 5 in our AP class. That was really not a good sentence, but you know, whatever. This is not a section that your notes currently have. I decided to kind of break the first section into two. So no, your notes aren't wrong. Well, they technically are, but no, they were not. Here we go. Heat flow. Welcome. All right, so on average, molecules in a warmer body will have more kinetic energy than one in a cooler body. Besides that grammar being just straight up wrong, you should know this. We talked a little bit last time about kinetic energy relating to temperature. In fact, we've talked for the last 3 units about kinetic energy being related to temperature. More kinetic energy means more temperature. More temperature typically we think of as being warmer. So, as molecules have more kinetic energy, they move faster and will collide more frequently because they're moving faster. Imagine a junior high class on a normal day of, boys and PE, and now imagine a junior high boys when you give them all energy drinks. They're going to be moving and tackling and falling and tripping and just being straight up annoying a lot more than they would normally. However, when molecules collide, they transfer energy as heat. This is actually a process called energy transferred as heat. Kind of a, original process. But when things collide, heat is transferred. Now, I'm pretty sure I say this, but heat is always transferred from high to low. Okay? You do not take your hand and put it on an ice cube and your hand get warm. That's not how science works. If you hold an ice cube, your hand gets cold. The ice cube gets warmer because your hand is warmer than the ice cube. So it's always going from high to low. Now, heat is neither a substance nor is it a verb. It's not. Okay, if anything, it's kind of a substance. But a substance cannot have a lot of heat. That's not possible. It's not something we could just have. I can't say, how much heat do you have today? Oh, I've got blah, blah, blah heat. No. And you also can't heat something up. Now, I know we say that all the time outside of chemistry, and when it really comes down to it, go ahead and say it all the time you went outside of chemistry. But inside the classroom, heat is not a verb. You can't just go heat something up. Instead, we can transfer energy as heat from a warmer substance to a colder substance, meaning we can transfer heat. It's less of a property that we can have and more of an object that we can hold. You can give it to someone. You can transfer heat. More so, you transfer energy as heat. Heat itself refers to energy. Okay? That you got to get that. Now, we call this type of energy, besides when we transfer energy as heat, we call it thermal energy, which hopefully should not be too big of a surprise. When tracking energy changes, however, we kind of come into this awkward issue. When you look back at basically your hand holding an ice cube, the question comes down to, is the ice cube getting warmer or is your hand getting colder? Now, your first answer is, well, duh, both. Thank you, you helpful student. That doesn't help chemistry because then we're saying, well, which one do we study? Generally, whichever part of something we are studying, we call that the system. And anything else affecting that is the surroundings. So in that case, if our system was the ice cube, okay, I'm going to, try and draw hand with an ice cube. Blue, make it look like ice. Okay, so if our ice cube is the system, then we are saying that heat is going from our hand into the ice cube. So we kind of got this heat flow going in. That's if ice cube is the system, or if our ice cube. If our hand is the system, okay, heat's going to go either way. If we look at the system as our ice cube, we're saying the system is warming up. If our system is our hand, our system is cooling down. So that'll matter very, very, very quickly. Systems will be focused on surroundings, everything else. So when energy is transferred into the system, it has to come from the surroundings. It doesn't just poof out of nowhere. So that will, however, result when it's transferred into the system in the surroundings having less energy. Basically, your hand gets colder if the system's the ice. Thus, the system itself has more energy, and the temperature of the system will increase. we call that endothermic. So, yes, your hand's made of ice. Wow. Okay, so back to the hand analogy. From the ice's perspective, if that's the system, energy is going into it. Thus, this whole process is endothermic. Heat is coming in. When energy is transferred from the system, however, into the surroundings, the system will have less energy. The surroundings have more, and the temperature will decrease. We call that exothermic. And well, you probably guessed it. From the perspective of the hand, this reaction is exothermic because heat is leaving the hand. So typically most reactions, from one perspective it's endothermic, the other perspective is exothermic. You can always have that. You can always have that. So typically that's why we have system and surroundings saying, in this case, what do we really care about? But again, if your temperature rises or you have more heat, endothermic, less kinetic energy, I was using that wrong, or heat is transferred out of a system, exothermic. Endo in, exo out. So let's practice that. A container of melted wax stands at room temperature. What is the direction of heat flow as the liquid wax solidifies? Is the process endothermic or exothermic? So you got a bowl of wax. Okay, the candle is melted and now it's liquid. So temperature-wise, that wax is stinking hot. The air is not stinking hot. That means that energy is going to be going out of the wax. Over time, and enough energy will leave the wax that it won't have enough energy to stay as a liquid. The bonds will then start condensing together, and you will eventually have a solid thing, a bowl of wax. Thus, the heat flow is going out of the wax, and from the wax's perspective, exothermic. Now, yes, we can be annoying and talk about, well, what about the air's perspective? Most of the time, it's kind of obvious what they're wanting you to be the system. Sometimes they'll designate, but in this case, you probably figured out they're talking about the wax. They don't really care that much about the air. True, they didn't specify, but I am saying that the system is the wax, and thus exothermic. There you go. All right. Since a substance is required to have its temperature raised in order to, however, melt or boil, that means the substance requires energy, and thus melting and boiling are endothermic processes. Pretty sure you knew that, but just wanted to make sure. Melting and boiling, and technically sublimation, though that rarely happens, unless you read The Martian. It's a very good book, by the way. Are endothermic processes. That is when you either go from a solid to a liquid or to a gas, just kind of going up that way. When a substance freezes or condenses, or again, technically deposition, though that doesn't commonly happen, the temperature will lower, thus energy is being released, and these processes are exothermic. So, the amount of energy required to vaporize or boil 1 mole of a pure substance is the molar enthalpy of vaporization. You will see this every now and then. You really won't do a whole lot with it. Just if I say molar enthalpy of vaporization, you probably should think, oh, that probably deals with vaporizing, which hopefully you're remembering is boiling. Cool thing is, the energy released when we condense it, which is basically the exact opposite process, has the exact same magnitude. So if I boil water, if I have water at, 50 degrees and then bring it to 100, and then I take that 100 and bring it right down to 50, the same energy released will be the same energy I had to use to actually get it to boil. All right, and the energy required to melt 1 mole of a pure substance is what we call the molar enthalpy of fusion, which is basically like the fancy word of melting, fusion. Never quite made a whole lot of sense to me, but there you go, fusion. And, hang on. Okay, there we go. This should be freezing. So, because the energy released when you actually freeze something is the same as the energy required to melt it. But again, molar enthalpy of fusion is when you melt it. There you go. As always, thank you for watching, and have a good day.